let's turn our attention specifically to sound. So if you remember, sound is a longitudinal or compression wave, which means that when a sound is created, there's a vibration, and that sets the particles that the sound wave travels through into vibrations so that they are vibrating to the left and right, parallel to the velocity of the wave. So we have areas of compression and decompression. At the head of the wave, the particles were compressed, and that would correspond to the crest of a wave. And then you have the areas of decompression, or rarefaction, which corresponds to the troughs of the wave. So, the distance between compression or the distance between two rarefactions, so from here to here or from here to here, would be considered a wavelength. And the amplitude would be the intensity of the wave, how strong it is. And then once again, we have period and we have, frequency and angular frequency. So once again, we know that the speed of the sound wave is equal to lambda f, and that for a constant speed, as wavelength decreases, frequency will increase. And that's the inverse relationship between those two. Now, the loudness of the sound wave is really associated with the amplitude. So the more amplitude, the louder the wave is. When you look at the formula for the speed of sound, it looks similar to the formula for the speed of a wave on a string. So remember, when we have a string that's vibrating up and down like this, that the speed is equal to the tension force divided by the mass per unit length. So it turns out there's a similar relationship, but it's in response to the materials, the properties of the materials that the sound wave is going through. So it's equal to something called the bulk modulus, which is basically how easily it is to compress the wave, and divided by the density, which is mass per unit area. So we're not going to actually use this formula, but you want to see that the speed of sound and transverse waves have a similar format. Also, sound is the speed of sound depends on the temperature of the air, because that affects the density and the bulk modulus of the air. And so it turns out that at 0 degrees, the speed would be 331 plus 0.61 times 0, or 331 meters per second. At 20 degrees Celsius, that is room temperature, it would be 0.61 times 20 degrees. So 0.61 times 20 plus 331 would give us 343. So the higher the temperature, the faster the speed of sound. We're going to use 331 unless you're given some other number. So, for example, if you know that a sound wave has a frequency of 440 hertz, and we use the speed of it as 331, we can find the wavelength using our speed formula. The wavelength would be this velocity divided by the frequency divided by 440 hertz, which is 1 over a second. So the seconds would be gone, and we would end up with meters. And I'm getting 0.72. 0.725. I think that's what that said. Yeah. Meters. And you could do it. You could find the frequency if you know what the speed of sound is. We're going to assume that speed of sound is 331 meters per second and that it has a wavelength of 0.50 meters. So we can find the frequency of that using V equals F times lambda, and F would be equal to V all over lambda, or 331 meters per second divided by 0.5 meters. The meters are going to go away. We'll be left with 1 over a second, which is a hertz, and it'll be 662 hertz. Okay, let's talk about that Doppler effect. Remember that the Doppler effect occurs because as a sound source moves towards an observer, so imagine that we have a sound source moving this way, and it's creating sounds. Those sounds on the front of it will be compressed, and the ones on the back will be decompressed. So on the front end, as it approaches you, you're going to hear a higher pitch because the wavelength is lower. And on the back end, you're going to hear a lower pitch because the wavelength is higher. Now, is it really changing? No, it's a perceived here frequency. And that frequency can be calculated using F equals whatever the frequency of the sound source is times the speed of sound, V, which is going to be 331 unless otherwise said. And VO is the speed of the person listening, the observer. And VS is the speed of the source that's producing the sound. So these are velocities, so we need to know which way the object is going. So if the source is going towards the observer, you're going to use a negative. Okay? You're going to subtract off the source. And if it is moving away from the observer, you're going to add it on the bottom. And the convention for the observer is positive here and negative as well. So when the observer is moving away from the source, you'll plug in a negative velocity. If it's moving towards the source, you'll plug in a positive velocity. So let's say a police car siren has a frequency of 500 hertz and it approaches you. So it's approaching you. So V of the source is negative 30 meters per second. And what is the apparent frequency that you'll hear? Well, you're just standing there, so your velocity is 0. So if I plug this in, it's going to be 500 hertz times the speed of sound, 331 meters per second, plus 0 because you don't have any speed. And then 331 meters per second minus 30 meters per second. So F is going to be 331 divided by 301 meters per second. So times that frequency. So 331 divided by 301 equals times 500 equals, you will hear 549 hertz. So that is indeed a higher frequency because it's coming towards you. Now, if it was moving away from you, this would turn into a positive, and you would be adding the 30 on the bottom. And so then you would be dividing by 361. And our new value would be 331 divided by 361 times 500. And it would be 458 hertz. All right. So once again, we talked about superposition of sound waves. And sound waves are really easy to hear that beat frequency on. If you get two waves that are very, very similar to each other, just a few hertz away from each other, They will have areas of constructive and areas of destructive interference. And the beat frequency is the rate at which you hear those constructive. It's the frequency of the constructive areas. So, for example, if you had F1 was 440 hertz and F2 was 445 hertz, the beat frequency would be 5 hertz. It's just a difference between them. And that means that you would hear 5 beats in 1 second. Okay, that's what that would mean. So sound intensity is how we measure how loud we perceive a sound to be. And since it is a pressure wave, it does carry a certain amount of energy. And it's actually a logarithmic function that we can use to turn it into a number that makes more sense to us. So if you've ever had a stereo system, you may see this unit dB stamped on it, and that's telling you the decibels of the sound. Okay, it's telling you how basically it's a logarithmic scale that it's using to rate how strong that sound is that you're hearing. The softest sound that we can find that has the smallest intensity. So the smallest intensity, I naught, is 10 to the negative 12. Okay, and it's going to be measured in newtons per meter squared or pascals. Sorry, not newtons, watts per meter squared. Remember, watts is the power of something, and we'll talk about that later on when we talk about electricity. So if you want to compare how intense a sound is to that base intensity, you would use this equation here. We won't really be making calculations with this, but we will be, you do need to understand that that's related to the amplitude of the wave, right? And you need to understand that the threshold of hearing, which is a sound level 0, has an intensity of 10 to the negative 12. A jet aircraft, on the other hand, if you're just 50 meters away, has a sound level of 140 and a sound intensity of 100 compared to what you would hear at the threshold of hearing. So if you wanted to find that intensity, it's pretty easy to measure intensity. Intensity is equal to the power of it in watts divided by the area. So think about, a sound wave. If you have a speaker making a sound wave, it's kind of over a certain distance, R, it spreads out, right? It spreads out. So if you were to look at, this is a side view of it, if you were to look at the front view of it, it would look like a circle to you. Hitting that sound wave would hit the wall in a circular pattern. So the area over which it hits far away is much bigger than the area if it's very close to your ear. And so this value here is really a value of finding the area of that. And then P is the amount of energy that's hitting it every second. So if I want to find that intensity, I need to know what the surface area is, and I need to know what the wattage is of that speaker. So if I do that, my intensity is P all over 4 pi r squared, which is 2.43 watts. And this is already the surface area. So it's 0.03 meters squared. So if I just take those 2.43 and divide by 0.03, then I get an intensity of 81 watts per meter squared. And then if I want to turn that into a sound level, decibels, then I could plug it into the formula from before. So of the intensity to intensity naught, or 10 times log base 10 of 81 watts per meter squared divided by 10 to the negative 12 watts per meter cubed. So let's see if I can find my log button on here. Okay, so this is going to be 81 divided by 10 exponent, actually 1 exponent, negative 12. I'm going to take log of that and multiply it by 10, and that's 139 dBs, decibels.